Okay, hello and welcome to some new slides on number theory and encryption. I have a lot of stuff to get across to you in this set of slides. It is going to take 3 lectures, not the normal 2. So there's a lot going on. There's a lot I have to show you. But at the very least, by the end, you will be able to laugh at this funny XKCD comic. Maybe you will be able to understand it right now if you've worked with doubles before. So this is a lot to do with numbers. So let's start with number theory. Let's get into division. I know we have to learn about division here in a college class. So let's figure out what our textbook has to tell us. What is new about division? So we have some new notation. We say that x divides y. I'm sure we've heard that before in a normal math class, but maybe not this symbol. So we say that x divides y, and you write it like this, like x divides y. You read the little pipe symbol as divides, if and only if x is not equal to 0, so it couldn't divide it, 0 divides nothing, and there is an integer k such that y equals k times x. So that makes sense. The flip side of saying that is there's a multiplication kind of thing going on. If x divides y, then y is a multiple of x. That's the flip side, and that's how you can turn that sentence around. So if x divides y, there's a way to multiply x to get y. And that, by definition, means that y is a multiple of x. And then you can also say, because x goes in cleanly in y, right? X is a factor of y, or a divisor of y. We say those things interchangeably. And a nice fun word that maybe you haven't seen before if you haven't taken a linear algebra class is a linear combination. It's going to prove to be very useful for the rest of our computer science careers. So a linear combination of two numbers is like you're writing the equation for a line from them. Like you have just the variables and then some constants out in front maybe. Linear stuff, not quadratic, nothing like that. No powers, just the variables by themselves, right? So a linear combination of two numbers, for example, is a sum of multiples of those numbers. All right? So 2x minus 42y, that's a linear combination of x and y because the coefficients out in front of x are like 2 and the coefficient out in front of y is negative 42. Okay? You're just kind of adding them together. So anything that involves two integers times your variables, like I don't know, how about negative 43 this time? Negative 43x plus 27y. This would also be a linear combination of x and y. X and y are taken to the first power, and then I'm multiplying those by some constant out in front that is a whole number. All right? Yeah, I guess it technically doesn't even have to be a whole number, but at least in this class I think we're going to care most about linear combinations with whole number coefficients. Okay, so yeah, those are some terms. Maybe we've heard them before. Let me show you a cool proof involving these terms. So we'll just unfold the definitions, and that will give us the proof. So let's pretend that we have 3 numbers, x, y, and z. They're integers, whole numbers, and we know that x divides y and x divides z. If both of those things are true, if x divides y and it also divides z, then x divides sy plus tz for any integers s and t. And what is this but our linear combination? So it divides any linear combination of y and z with integer coefficients. So there's linear combinations popping up. Good thing we talked about them on the previous slide. So yeah, here's the proof. So it's an if-then statement. So assume these things are true, and then prove that this thing is true with a direct proof. All right. So we'll just use the definitions. So if we know this, x divides y and x divides z, what does that mean? Well, I know that the thing that is dividing is not equal to 0, and the other thing is a multiple of the original thing. Okay, so let's write that in words. So if x divides y, I'm assuming that, then I know that y is equal to some k times x, where k is an integer. Okay, and if I know the same thing is true about z, if x divides z, then x is also a multiple of z. So z is equal to, it doesn't have to be the same k, it could be like an m. Z equals mx, and that's another integer for some. So these two things are true at the same time for some ints k and m. All right, so that's what I get by assuming these things, and now I need to assume them to prove this. X must divide any linear combination of those two numbers. All right, so my job is to show that x divides all this, which means I need to find something that is a multiple. Right, so here's what I need to show. If I spell that out involving the equality, what I need to show right now is that sy plus tz, right, just kind of extrapolate, is equal to some other multiple of x, right? It's equal to like r times x, rx. And this is supposed to work for any s and t. Crazy. For any s and t. And so not only was there like a universal quantification over these x, y, and z's at the start of this proof, there's also a universal quantification now that we've gotten to our conclusion over this s and t, which is crazy. All right, so this is what we need to show though. So for any s and t, this is true given what we know so far. All right, and how do we prove it for any s and t? Well, your standard for all proof. Let s and t be arbitrary. If it works for anything, if they're arbitrary and it always works, then it works for any s and t. Be arbitrary int. Now I need to show that this holds no matter what s and t were. All right, so sy plus tz, sorry, that looks like a 2, that's a z, tz equals, well, what do I know about y and z? Ooh, I have some equations on them. So it's really just plugging and chugging. So s times, what is, let me use parentheses, what is y but kx, plus t, and what is z but mx, ooh, which is equal to, can I factor an x out of this? Yeah, it's there twice. See where I'm going with this? X times sk plus tm, so I factored an x out. And so what do you know? I have, which is equal to, like if I just rearrange these, I need something times x that equals this original thing. I think this looks like something times x, and that equals my original thing. Let me just spell it out for the reader of the proof. Let me put it on the left. sk plus tm times x. And what do you know? I have something that is an integer. See that? So it's a product of integers, and I'm adding those two products together. It's still an integer at the end of the day. This can be my r. This can be my integer that equals, it's a multiple of x. So when I multiply it by x, I get sy plus tz. Oh man, started there, ended there. That's exactly what I needed to show. And that proves, right, what we needed to originally show, that x divides sy plus tz. That's what it means to divide something. You end up with a multiple. Okay, I hope that makes enough sense. So therefore, x divides sy plus tz. QED. Mic drop. So that's a fun little proof, and I think we're going to use it later. So keep that in mind. All right, so now I have a question for you. Maybe go back to this slide with the definition. You can pause it here if you'd like. But is it true that 7 divides 21? Yes or no? And I'd like you to explain your answer using that definition. All right, so give that a try. I think it's pretty obvious that yes, of course 7 divides 21, but why? Why is this the answer? Well, you need to be able to express that 21 is equal to 7 times something. Like it has to be some k, right? K times 7. And 21 is equal to 3 times 7. And that can be my k. Does that make sense? And also we need to prove that 3 is an int. Like it's an integer multiple of 7. 21 is. And 3 is an int. I think that's pretty obvious. Don't have to prove that. It is an int. And also technically it's not 0. So 7 is not 0. That works out as well. Okay, so that's kind of just applying the definition. You show this equality holds, you show whatever you need to have as part of it, and it all works out. So that is why 7 divides 21. We're getting very, very technical with our basic division. All right. So with that in mind, let me give you something a bit more challenging. Okay, so here is a proof that I'd like you to try, and then I'll show you my way. So universal quantification. So assume you have all these 3 integers, a, b, and c, they're whole numbers. If these two things are true, if a divides b and a divides c, you can assume those, right? Direct proof. Then you need to show that a squared divides b times c. So it's kind of like you can multiply these two rules together and somehow keep everything on the same side, and you have a divisibility proof still. Isn't that cool? So give that a try, and I will show you my way if you get stuck, or just to confirm your assumptions. All right, so here's the proof that I think is good. So we need three integers, a, b, and c. We're universally quantifying over them, so let's get some arbitrary ones. Let a, b, and c be ints. We need those. And assume this, prove this. So in assume a divides b and a divides c. All right, so I got those two things just taken for granted. I'm assuming them. So let's unfold these definitions now. So I know that b is equal to some multiple of a, so b equals ka, let's say. And I might need room. And c equals some other multiple of a, so I don't know, k and j times a, for some ints k and j. That's just unfolding the definitions of divides for some ints k and j. Okay. Now what do I need to show? I need to show that a squared divides b times c. So need to show, what is that inequality form? It's like show that bc is equal to some integer multiple, call it r, of a squared. All right, I need to find some r now. And some integer r could be anything. I just need to show that this is possible. All right. So let's work our way backwards again. So I know that BC is equal to, well, here is something that I can plug in for B. Here's something that I can plug in for C. It's KA times JA, and ooh, see what's going on here? That I can factor out an A, or I can bring out an A twice. That's KJ times A squared. And this is a multiple of two integers, which is itself an integer, and I could pick that for my r. And now I have an integer multiple of a squared that gives me BC. Started with BC, integer multiple of a squared. That's exactly what I needed to show. Okay, so therefore, a squared divides b times c. Isn't that cool? So essentially, you can multiply a divisibility proof on both sides, just like you can multiply equalities on both sides. That's fun. That is useful for us. All right, so we're talking about division. Let's have a very important fact about division now. It's called the division algorithm. So this tells us exactly how integers divide and have quotients and remainders left over. Q for quotient, R for remainder. So here is our algorithm. Let n be some number that you are trying to divide, some integer, whole number, and let d be a positive integer. The d is the thing you're dividing n by, okay? Then this proof is showing us that there are unique integers. There's only one possibility for both of these, called q and r, with r being between 0 and d minus 1, no bigger, because otherwise it wouldn't be a proper remainder, right? It would go in one more time. So the remainder must be between 0 and the number that you're dividing by minus 1, such that your original number is equal to the whole number quotient, like the integer division result, times the thing you're dividing by, plus the remainder. That's what it means to divide something, all right? So maybe you've never really thought about it like this, and that's cool. But this is totally provable and totally useful to us. So essentially, in words, it's like you're trying to do n over d. If you try to divide n by d, then that equals q, and then you have a remainder r left over. That's what this is saying. All right, so that's what all these terms mean, and that's why the equality makes sense. It's like n equals qd plus r. Yeah, hopefully that's apparent. So yeah, so q is the quotient, we call it, and r is the remainder. And I think I write that right below anyway, again, but might as well write it twice. Very important. We care about remainders a whole lot in computer science, right? So in this algorithm, q is the quotient, r is the remainder, and these, if you would just like the q or just like the r, we have, you know, the mod, right? You know that is our plus sign in C++. The alternative, the integer division in math land, is called div, okay? So q is equal to n div d. That's the operation. That's the mathematical operation. Div is doing integer division. It's dropping the remainder, or the decimal places. What is math but another programming language? This is its syntax for integer division, and here is math's syntax for modulus. It's like pretend that mod is the percent sign. It's getting you the remainder, right? And mod d is equal to that remainder. And so here are some examples. let's see here. 7, if you div that by 3, well, it's 2 point something, right? It goes in twice with a remainder of 1, yeah? So the answer is 2 for div. That's integer division. 7 mod 3 is equal to 1, because there's one thing left over. It goes in twice to make 6, and then there's one thing left over that makes 7. And the reason this works is, and the reason these are the correct answers, is because 7 is equal to 2 times 3 plus 1. And that is, we just spell it out using these terms. It's 2 is the quotient, 3 is the divisor, the thing we're taking, that we're dividing by, and 1 is the remainder. And this remainder, these are unique integers. The remainder can't be anything different because it can't be bigger than the number 3. It can't even be equal to 3, because otherwise it would have gone in one more time. There would have been a bigger quotient. All right, if you think about this long enough, these are the only options for Q, D, and R that make 7 according to this rule, these side conditions that we have. Okay, so that's equal to 6 times 1, of course, which is in fact 7. So that it checks out. That's what it means to divide numbers. You can always divide integers by another integer that's non-zero and get some unique quotient and some unique remainder. That uniqueness is important. Okay? All right. So with that, you can do fun math by taking modulus all the time, which is kind of fun. So we have numbers that wrap around in our everyday life and we love them. We'll need this in math too. Like, you have a clock. 12 wraps around to 1. And so on and so forth throughout the day, right? So we can do math with numbers that look like clocks that wrap around, all right? So let me prove that to you. Modulus, numbers that you can take the modulus of, those also wrap around. So if you take some number, m, that's your modulus, and you always do mod m, like you say, give me the remainder after dividing by m, after you do every single calculation, you end up with what's called modular arithmetic. Your answer is always mod m at the end, and that means the only numbers that you end up with after the end of your very long calculations are any number that you could get by taking the remainder, right? If as you're doing mod m, the only results that you could get back for the remainder are 0, 1, all the way to m minus 1, because if it went in m times, it would go in cleanly and it would be back to 0. It flips itself over. All right, so let's pretend we're doing math and we're working mod 5, for example. 0 mod 5 is, of course, 0. 1 mod 5 goes in 0 times with 1 left over, all the way down to 4 mod 5. That's equal to 4, of course. But that's the last possible remainder you could have after doing mod 5. Once you get to 5 again, now it goes in once, and there's 0 left over. You see the 0 repeats itself? If you do math and you always do mods the same number at the end, your numbers will repeat. So then, like 6 mod 5, there's another way to get 1. So if you always do mod 5, like you don't know if your answer was, if your original number was 6 or if you knew that it was 1. They still give you the same remainder, all right? So sometimes that's all you need, but remember what you can get back. When you do modular arithmetic, when you take the mod by some m at the end of every calculation, your numbers are only going up to m minus 1. All right? That's what it means to be a remainder. It can't get any bigger than the thing you're trying to divide by. It can't get equal to it either. Okay, so sorry I had to spell that out for too long maybe, but it's something I want you to remember. All right, so now let's move on to doing those kind of calculations. We say that we're working mod m, mod some number. I was working mod 5 up here. All right, so if I'm doing, I can do addition mod m by just doing my addition first and then taking a mod afterward. It's really just do your calculation, then take a mod at the end. So like 4 plus 3, I can work mod 5, and so that's equal to 7, right? 7 mod 5, which is equal to 2. There's 2 left over, all right? You can do the same for multiplication. Just do your multiplication first, and then take mod whatever you're trying to take. So like 4 times 4 mod 5. Do your multiplication first, and then shrink it down. It's kind of like a hash table. 6 mod 5. Sorry, 16 mod 5. And there's 1 left over, right? Because it goes in 3 times to make 15, and there's 1 left over. That is your modulus. So just do the calculation and then do mod m right after it. That's really all it is. That's modular arithmetic. We have a very fancy word for it because it's so important. All right? here is some more modular arithmetic. You can make, just like you made normal like multiplication tables in elementary school and addition tables before that, you can do the same for modular arithmetic, but your tables are much smaller and they're finite. In fact, you run out of options. So that actually makes math a bit easier if you only need that many numbers. So if you like to use mod m after the end of all of your stuff, like for example, if you're doing multiplication, addition, mod m we say, then if you're always doing mod m at the end of your calculation, you usually say that I'm working in Zm, all right? And Zm is just a restriction of the integers, because that's what Z is, such that it's the result of taking the modulus by n. So it's any number that you can get after you take mod by n that was an integer originally. So 0, 1, 2, all the way to m minus 1. Those are the only numbers in Zm, we say. So we say we're working in Zm. That's equivalent to saying we're working mod m, okay? Hopefully that makes enough sense. So for example, here are the mod 5 addition and multiplication tables. You only have 5 numbers in mod 5 land, right? Those are the only numbers that exist in Z5. So here's what it means to multiply them. Like 2 times 2 is 4, 2 times 3 is 6, but mod 5, that's 1. Right? So they all repeat themselves. It doesn't matter if it was like 200 times 300, that would have been shrunken down to like be 0 times 0. That's just 0. All right? If you try it out, hopefully it makes enough sense. And then addition works the same way. It's like, all right, 3 plus 4, that's 7, but we're working Z5, so you do mod 5 at the end of that, so it's 7 mod 5, that's 2. All right? And so there's a finite number of numbers. There's only 5 numbers in each row and column. So there's only 5 numbers in Z5, okay? And so we have a bunch of numbers that are equivalent to each other. We say that 2 numbers are equivalent to each other after we take a mod by saying that they were congruent, all right? That's the fancy term. X is congruent to Y in the mod m land when if you start with X and Y and you take mod m's, you end up with the same result, even if X and Y weren't originally the same number, okay? They used to be different, but now they're the same mod m, so we say that they're congruent rather than saying that we're equal. So use the equivalence symbol. They're like, X is equivalent to Y. It's congruent to Y. That's another way to pronounce that symbol. X is congruent to Y, and then we put mod m in parentheses, all right? So here are some examples. 0 is equivalent to 5 in mod 5, right? Because take mod of both of these, you get 0. 0 is equal to 0. Therefore, they are equivalent up to, they were equivalent in Z5. They're the same number. Likewise, 5 is congruent to 10 mod 5. Again, you take mod 5 on both of those, you get 0. Same with 15 and, that's supposed to be 5. 15 and like 55. Again, those are all 0 mod 5. So mod 5 goes in parentheses and it all works out. And then you can do the same for things that are remainder 1. So 1 is equivalent to 6, is equivalent to 11, right? Just all those multiples, all those, keep adding 5s, and you have all the numbers that are equivalent to each other, mod 5. Okay? So obviously 1 is not equal to 6, but it's congruent to 6 in mod 5 land. Same with 11. All right, and I hope these symbols are making a bit more sense now that I've thoroughly talked about them. But this is going to be useful for us. Like in computers, we have integers that are finite. So really, we're doing mod 2 to the 32 arithmetic when we're working with unsigned ints. You just never thought of it that way. This is why we have this class, okay? So here's a fun theorem, and it has to do with all this stuff, and it's going to hopefully make things make slightly more sense, because I'll be using those definitions, all right? So here's the fun trick. You can do mod m on each number before you do the plus or times. This was saying up here, like, you had to do the plus first, the times first, and then do mod m. Well, actually, you could have done mod m on the individual numbers and then taken another mod m. That would have made your result a bit easier to get, all right? So you can do mod m on each number before you do plus or times, and you still get the same result, which is fun. What that means is you're allowed to make your numbers small before you do any of your operations, all right? So here's an example of this theorem, and then I have to prove it for real. This is just an example of it. It is a true theorem, though. So pretend that we wanted to do 77 times 63 mod 5. we want to know the answer to this big thing, mod 5. And, well, let's go to Python, and let's see what it really is. Python, it's, what was it, 77 times 63? Oops. That's 4851. And then we wanted mod 5 of that. So the answer is 1, but we didn't have to do our long multiplication. We could have actually taken mod 5 of 77 and 63 first. All right, so here's how that works. 77, you could have done the mod 5 first, is what this theorem is saying. Do mod 5 now. 77 mod 5, 63 mod 5. And now I don't have to bring out like Python or a calculator, because I can do these individually. And then I take that result, mod 5. All right, that's equal to, what is this? 77 mod 5, well, it's got 2 left over. I can do that in my head. That's 2 times 63 mod 5, that's 3. And then do that mod 5. Oops, I need more room. 2 times 3 mod 5, which is 6 mod 5, which is 1. Which is 1. Which way would you rather do it? You can save a lot of work by taking the mod of those bigger numbers first, all right? And this theorem is saying you can always do it that way. Take the mod of the bigger numbers, shrink them down, and then do mod 5 again at the end. Isn't that cool? So you can make the numbers small before you do any operations. And I would like to show you the addition case, because the multiplication case is very similar to that, and I think you could do it at that point. We will need the lemmas on the next slide, but let me just at least write out the theorem first. So theorem, here's the addition case of this theorem. It's like x plus y, if you have 2 numbers, and you're taking mod m by them, that is equal to, first do mod m on these individual numbers. First do x mod m, and then do y mod m and add those. And then do mod m at the end one last time. Looks like more work, but technically it's less. I think you could see that I was able to do that one in my head without having to do very long multiplications. So this is what I want to prove, and the way I'm going to get there is with a little helper lemma here. So this lemma is just something very important that is kind of obvious from the definition of everything. I'm going to show you that x mod m, like if you're trying to calculate that, that's equal to x plus km for some integer k. Now let's prove that using the definition, all right? The definition of mod. So let's pretend we have some number, we're calling that number x, and we're trying to divide it by m, right? Because we're working mod m. What does it mean to do all those things? Well, if you just look at those definitions again, like use this, replace r with n mod d because it's equal to that. Right? If you just shuffle around some of these variables and rename things, you will end up with this equation right here. Here's the number you have. You're trying to divide it by m, right? So you have some integer multiple of m. There's your q, I is q. And then your remainder, you have some integer multiple of m plus your remainder left over, right? Every time you take the mod by m, every time you divide some x by the number m. You have some integer times m plus your remainder that all adds up to x by the division algorithm. You're trying to divide your number x by m, all right? I've just renamed some things. So this equation holds. We can solve that, right? We can solve that because that needs to be on its own. We can solve this equation for x mod m. This is a very, kind of obvious fact, but it's going to be very useful on the previous slide. So x mod m, it's equal to x minus im, right? Let's bring them all to one side. And I need to show, I've almost showed that x is equal to km for some integer k. I know that it's minus some integer m. Here's how you fix that. It's just be like, let k equal negative I. And now, just by funny math, then x mod m, if you plug in k for negative I, then x mod m is equal to x plus km. Isn't that funny? So there's just another integer. I've made a positive integer this time that I can call k, and I can add that by multiplying it by m to x to get x mod m. All right, so I've just solved for the remainder. Here's how you get it. Therefore, right, I found some integer multiplied by m added to x equals the remainder. So the remainder of any number, when you divide it by m, x mod m, that is equal to your original number plus some integer multiple of m for some integer k, which is funny and weird to think about. Let's use this in an example. Like that is the proof. We really just proved it. But here's what it means. It's like, all right, if you're trying to do like 11 mod 5, for example, what we've just proven is that that's equal to, right? It's equal to the original number minus some integer multiple of your modulus. And this integer multiple is essentially the quotient, negated, kind of. So the quotient was 2, I'm negating that, and I got minus 2 times 5. That's what 11 mod 5 is equal to, because that's equal to 1. Right? 11 mod 5 is 1, there's 1 left over, that's equal to 11 minus 10. But now this is in terms of my original number and my quotient. All right? That's how I can find another way to equal the remainder. And this fact that I know this, for some integer k this is true, that I can find it if I need it, that actually makes a very powerful tool for this theorem, believe it or not. Let's use it now. All right, so if I know this is all true, or this is what I'd like to be true, let's figure out what's going to happen. Because, all right, I'm trying to do all of these things. I'm trying to prove that this side is equal to this side, and I'm doing a bunch of mods in the process, all right? I'm taking these mods. I'm doing x mod m and y mod m. Because I did those, I know that this theorem holds, all right? So what is x mod m but? So what do I know after I do these operations? I know that x mod m, by my lemma, that's equal to x plus km. I'm just reading off the definition, what I just proved, all right? It's equal to x plus km for some integer k, and that's really going to make all the difference here. And then I also know the same for y, because I'm taking mod m for that one too. Y mod m, that's equal to y plus km. No, sorry, not km. Could be some other integer, of course. Can't be the same one. I have to use a new variable. And this is true for some integers. Don't care what they are, just know that they're there for some k and j. All right? So that's there. And now let's take this side and unravel it using these facts that I know from the lemma. All right, so x mod m plus y mod m is, and then I'm doing mod m at the end of that, right? Mod m, that's equal to, well, all right, let's replace this. X mod m is equal to x plus km. Is equal to x plus km, sorry, there's a ton of parentheses here, plus y plus jm mod m. Can't forget that. So that's true. And then let's bring like together. Like I have some multiples of m. Let's bring those together and put x and y next to each other. So this is equal to x plus y plus some multiple of m times k plus j, right? K plus j. And then I'm doing mod m here. And it just so happens that this part is going to go to 0. This entire part is going to go to 0. And let me prove that to you. Let me just do something random here. If you have a number and you add to it any multiple of the thing you're taking the modulus by. Let's pretend I'm doing all this work, mod 5. This plus 77 times 5 does absolutely nothing to this number. Does that make sense? Because, like, if you had 1, that's equal to 1 mod 5. If you had 6, that's equal to 6 mod 5. Like if I add a 5 to 1 and take mod 5, it's still 1, right? This 5 does nothing. It just wraps back around like a clock. All right? That's the key here. This all goes to 0. This times 5. Any multiple of the thing we're taking the modulus by goes to 0 because we're just wrapping around the clock back to 1. The answer is immediately 1 here. I hope you see that by this. Like 1 plus 5 is 1 mod 5. 1 plus 10 is 1 mod 5. It just the 5 multiples go away. And so all that we're left with is this small guy. All right? So we were doing the same thing here. I have some multiple of m, and I'm taking mod m afterwards. So that multiple is going away. The whole side is going away. So all I have left now is x plus y mod m. And what do you know? Here's this side. Here's this side. That's just this equation backwards. And that's exactly what I wanted to show. All right? So that is a weird little proof, but it goes through, and it shows that you can do multiplication. Well, the multiplication version is the same kind of proof. I did the addition version. It shows that you can do your addition after you take the mod of both sides. Like if this was 77 plus 63, take these mods, then do the addition, then do mod 5. All right? So that's a fun little proof. I hope it made a little bit of sense. Your book has it too, so me explaining it and you reading it there too, I think will cause it to sink in. All right? But it's a fun, neat little proof. It'll save you a lot of time, right? I think it was obvious that this equation, I could do it a bit faster if I took the mods first. All right? So that was our lemma. And let's see here. Here's an example for you. I haven't shown you anything involving negative numbers, but if you go back to the definition and the requirements on your remainder, see if you can figure out what these are. What is 33 mod 7, and what is negative 33 mod 7? All right? Give that a try. Show your reasoning. This one should be easy. That's a positive number. That all makes sense. 33 mod 7, well, just using your division rule, 33 is equal to, well, some multiple of 7. How many? Goes in like to 28, right? 7, 14, 21, 28. 35 would be too big. So 28, which is 7 times 4, goes in 4 times plus 5 left over. And I need to show that like this 5 is our remainder. That's the thing you get back when you use mod. I need to show then that it is like, it's between, this 5 is between like 0 and strictly smaller than 7, right? And this uniquely better add to 33, all right? So that is the reason why 33 mod 7, therefore 33 mod 7 is equal to 5. There's 5 left over. So that's the answer. And this is why. Go back to the division rule. Show that it breaks down in this way. This is the only thing the remainder could be to have this still work. Okay? Let's see here. Sadly, this one, if you do this in C++, I think it might give you the wrong answer. Some programming languages, like, don't go straight to Python or to C++ for this. I think Python does it right. Negative 33 mod 7. Okay, that one does it right, but I think C++ does it wrong. It'll give you a negative answer. Some programming languages don't follow the definition of the division algorithm. Don't follow the definition. Don't follow the requirement, let's say, that your remainder better be between 0 and strictly smaller than the thing you're dividing by, your divisor. So I think C++ will give you a negative modulus answer, a negative remainder, and we don't want that. That's wrong. It's not what it should be. It's supposed to be between 0 and 1 less than the divisor. So with that in mind, let's make negative 33 the right way. It's equal to something, right? It's something times 7 plus some remainder, and that remainder better be between 0 and d, and d is 7 here. All right? So the only way that this works is you go a little too far in the negative side. Like you go to negative 35. Negative 5 times 7, that's negative 35, and then you need to bring it back with a positive number, right, to negative 33, so plus 2. So this is the reason why, and this 2 has to be within that range between 0 and 6 if you're doing mod 7. Therefore, negative 33 mod 7 is equal to 2. It's the number 2. I think C++ gives you a negative answer back. I think it would have been, I believe if you do this in C++, it will give you 2 minus 7. It will give you back negative 5. And that is not the right answer. It's congruent to the right answer, follow the clock, but it is not division algorithm definition of the remainder. Okay, so that is, for this class, this is what you must give back. Negative 33 mod 7 is 2 and only 2. That's the right answer. Okay, I hope that makes sense. With that in mind, and also this theorem in mind, wink wink, try this. You can do it. I promise that you can do both of these without going to a calculator, without going to a programming language. See if you can figure out the tricks, right? So calculate this guy mod 6 and this guy mod 7, right? use your rule where you can take, if you're doing a bunch of multiplications or additions, you can take the modulus first before you do them. So here are the tricks. Let's see, this is, what is this but 44 12 times, and it's a bunch of multiplications. So I can take 44 mod 6 before I do all those multiplications. All right, so this is equal to, first do mod 6, 44 mod 6, and then take that to the 12th power. All right, 44 mod 6, it's 36, 42, so there's 2 left over. So it's 2 to the 12. And again, at the very end of the day, you have to still do mod 6. That's where your answer lies. So 2 to the 12 mod 6, and now you can do some math tricks to make this easier on yourself. What is 2 to the 12 but 2 to the 6 twice? Still mod 6. Let me write mod slightly better. Mod 6. And then what is 2 to the 6 but 2, 4, 8, 16, 24, 2, 4, 8, 16, 32, 64. There we go. It's 64 times 64 mod 6. This is a multiplication. I can take mod 6 first before I do the multiplication. So what is 64 mod 6? It's well, it goes into 60, and then you have 66. So I guess 60 is the closest one. 10 goes in 10 times with 4 left over. So it's 4 times 4, right? I took the mod of 64 twice. That's just 4 mod 6. And then I do mod 6 at the end of that. So that is finally equal to 16 mod 6, which is equal to 4. And that's so much better. That's easier than calculating 44 to the 12th power and then trying to do division. C++ can't even like manage that, but Python can. Giant number, and then you can do division. It really does work out. This giant thing, mod 6. It is 4 at the end of the day. The answer is 4. Okay, so that is a fun example. Hope you got that one. Let me draw the 4 better. It's bothering me. And now this one, 5 to the 6th power, mod 7. Hopefully this is making enough sense to you. It's just a bunch of 5s, but 5 doesn't go away when you do mod 7. 5 mod 7 is still 5. But here is the trick there. This is equal to, what is 5 to the 6th but 5 squared cubed? Ooh. Then you still mod 7 at the end of all that. What is 5 squared? That's equal to 25. And then we just take that cubed, right? So it's 25 times 25 times 25. Again, mod 7. So that's what we're working in. We're working in Z7, right? And what is that? But what is 25 mod 7 now? Because I can take those, take it mod 7 before I multiply. 7, 14, 21, and then you got 4 left over. So 4 times 4 times 4. Again, mod 7. Mod 7, which is equal to 64 mod 7. So it's 16 times 4 is 64. And then 56, 63, right? And then there's 1 left over. So you can really do it in your head if you remember your multiplication tables. So this answer is 1, and it's much better than doing 5 to the 6th power. Oh, sorry, that's exclusive or 5 to the 6th power, and then trying to divide. Right? This is much cleaner, and it's much more efficient if you ever needed to calculate this in a program, right? Also that. So think about that. Keep that in mind. With that, I have 2 more slides for us today. So let's talk about primes, and I'll show you one cool feature of primes, and then we'll save the rest for next time. So again, definitions you already know. Let's just spell them out because we're going to need them for this class. All right, so a number p, we picked a very special variable name to mean something, right? A number p is called prime if it is an integer greater than 1, so it's a whole number, it's bigger than 1, can't be 1, 1 is not prime, and its only factors are 1 and itself, all right? So that's the only way you can make it. A positive integer, if it's not prime, we call it composite, right? And if you just negate this, what does it mean? Well, that means it has a factor other than 1 or itself, if it's composite, okay? So that's what prime and composite means. I'm pretty sure you remember those definitions already, but here are some other terms that you maybe have not seen. So greatest common divisor, or GCD, that is the biggest thing that goes into 2 numbers. So you take the GCD, the greatest common divisor, you find that of 2 numbers at once. So the greatest common divisor of x and y, it's the largest positive integer that's a factor of both. And so let's say I want to find the GCD, the greatest common divisor of 12 and 18. Well, the way you do that in math is, maybe you learned this, was you just factorize both of these. That's equal to 2 times 2 times 3, and 18 is equal to 2 times 3 times 3. And you just highlight whatever they have in common, like you pick as many things as they have in common. So there's a 2 times 3 shared by both 12 and 18. And so that means that's the biggest number. 2 times 3 is 6. That's the biggest number that divides cleanly into both 12 and 18. So 6 is the GCD of 12 and 18. Not 12 and 18. All right, that's how you find it in math, at least. There's a fancier algorithm that will find it more rapidly than having to do prime factorizations, but it is defined mathematically in terms of primes. And then the least common multiple is kind of like the flip side of that. The least common multiple of two numbers, again, you give it two numbers and you find the least common multiple of those particular two numbers. It's the smallest positive number that is an integer multiple of both. So it's a bigger number. Like GCD was a smaller number that divided cleanly into both of them. The least common multiple is a larger number, maybe the same as one of them. It's a multiple of each of them, so it's a bigger number. It's an integer multiple of each of them, the smallest one that they have in common. All right. So let me show that to you. Let's try and find the least common multiple of the numbers 6 and 8. And so what you do is you just start taking, you start going down the multiplication table. Like it goes 6, then 12, then 18. What are all the multiples of 6? 24. And then what are all the multiples of 8? 8, 16, 24, and eventually, not 27, eventually you find a match. 24 is the smallest multiple of 6 and 8 that is shared by both. All right? So that, therefore, means that 24 is the least common multiple. That's how you find it. It's the LCM of 6 and 8. It's the smallest thing that is a multiple of both. Okay? I hope that makes enough sense. And then two numbers, we say, are relatively prime. This is involving the GCD. Two numbers, we say, they don't have to be exactly prime like a normal prime number, but they're prime relative to each other, we say. Two numbers are relatively prime to each other if their greatest common divisor, like their shared factors, is nothing other than 1. All right? That means they share no factors. So from each other's point of view, they're prime to each other, I guess. Share no factors. It's a weird little definition, but it will make sense the more examples I give you. Share no factors. That's what it means to be relatively prime. And so, for example, 7 and 12 are relatively prime. Even though 12 is not a prime number. 12 is equal to 2 times 2 times 3, and 7 is equal to 7 times 1, right? They share no factors. That's what it means to be relatively prime, even though 12 is not itself prime. All right, so relatively prime means nothing about primeness. So the two numbers do not have to be prime, okay? How do I want to say that? Relatively prime do not have to themselves be prime. Don't have to be prime. Themselves. I hope that makes sense. So like 7 and 12, they're relatively prime. 12 is not a prime number, but it's relatively prime to 7 because it shares no factors. All right? So two numbers can be relatively prime to each other and both be composite numbers. It's totally possible. All right. Yeah, so that is a bunch of definitions. Let me end this lecture by giving you the coolest, one of the coolest theorems there is in this class. All right? So this is like the classicest of the classic theorems. There are an infinite number of prime numbers, and we are ready to prove it. I'm excited for us. So here is kind of the intuition behind this proof. Hopefully this intuition will cause it, when I write it down, to make enough sense. Here are a bunch of prime numbers multiplied together. I don't care what the answer is, but if I take them and I multiply them all together and I add 1, is it true that whatever that number is, whatever this result is it divisible by any of these, 2, 3, 5, or 7? Because I took their multiplication, I multiplied them all together, and then added 1. So is that final answer divisible by any of those original 4 numbers? And the answer is no, right? Because if you take the remainder, if you do division, there's always 1 left over. I added 1. So it doesn't go in cleanly if you divide by any of these individual numbers, all right? That's going to be the trick to this proof. That kind of idea, all right? So this is a classic proof by contradiction. So there are an infinite number of primes, so a proof by contradiction starts by assuming the theorem is false. Assume the theorem is false, and we'll find a contradiction. We'll eventually use the fact that every number is a multiple of its prime factors, all right? So, all right, assume the theorem is false. We're trying to prove that there is an infinite number of prime numbers. So assume otherwise. Assume, therefore, that there's a finite number of prime numbers. Assume there are a finite number of primes. And we're going to find a contradiction there. Obviously, we know there's an infinite number of prime numbers, but this is how you prove them. Assume there's a finite number. If there's a finite number of prime numbers, then you can list them all out, like 2, 3, 5, 7. Eventually the list ends, right? It's finite. P1, that's the first prime number, that's 2, P2, P3, all the way to Pn. If there's a finite number, there's a last biggest prime, all right? That's what has to be the case, right? If there's a finite number of prime numbers, there has to be a last one. That's the last prime. We're going to derive a contradiction from this, all right? So, all right, if these are all the prime numbers in the world, consider this number. Consider k, we'll call it k, equal to, multiply all your prime numbers together. You made me a list. Use that list. Multiply every prime number on that list by itself, all the way to Pn, and then add 1, this idea, plus 1, all right? So we're saying that this is a number, right? We can make it. We can multiply all these numbers together and add 1. This number is not a new prime number, right? Because it's bigger than the last prime, so it has to be a composite number, which means all these things fall in line. This number, k, whatever it is, it must be a multiple of primes, right? That's what every number is. Every number is a multiple of prime factors, so it better be, whatever k is, it must be a multiple of a bunch of primes that you put on this list, of all the primes that are on this finite list. It must be a bunch of primes, because it must have prime factors, right? Because it's not a prime number, that's for sure, because it's bigger than the last prime. A bunch of primes from the list multiplied together. That's what it means to be a multiple of prime factors. Together. All right. But notice, with the same idea, if you try to divide any of these, like if you try to divide this k by any of P1, P2, P3, all the way to Pn, there's always 1 left over because I added 1. Ooh. All right, but none of. All right, it's just obvious from math. None of those primes actually divide this number, but none of P1, P2, all the way to Pn divide k. I made it, so that's impossible, right? So, what can we conclude then? If there are no factors, there's no prime factors of this number k. So, either, none of those numbers divide it. Either k itself is prime, right? What are our options at this point? Either, if we have no factors out of any prime numbers, then k must be prime itself. Either k is prime, it's a brand new prime number. That's what it means if it has no factors. That means it's prime. Or there's some other prime that we didn't put on the list and would have gone into it, right? Or there's some prime on the list that would have divided this that we forgot about. Or there, either k is prime or there's a smaller prime we forgot to list. Those are your only two possibilities, right, if you think about it long enough. There's a smaller prime we forgot to list. That's the only way. Like, this is a number. You can build it. If it doesn't go in by any of these primes, then either it itself is prime, because it has no factors, or it does have a factor. It does have a prime factor, but we accidentally forgot it on our list of all the primes. All right? Either way, either if k is prime or there's a smaller prime that we forgot to list, we claimed that we wrote down every single prime in the universe. Right? We claimed that we did not leave anything out. In either case, we left something out. That's our contradiction. I hope that makes sense. All right? Contradiction. No matter what, there's a prime not on that list, so you cannot list all the primes. Therefore, our initial assumption of them being finite is wrong. Therefore, there's an infinite number of them. That is the beauty of proof by contradiction. It's like, it makes no sense. We find something that makes no sense, and then somehow that just means the entire theorem goes through. And that is beautiful. All right? So that's like one of the best theorems I'll get to prove to you in this class. Please yell at me in office hours if it didn't make sense. This is just so magical and so beautiful to me. So that's where I want to leave us today. We'll come back next time, talk a little bit more about primes, get into some cooler theorems, but this was definitely a classic. Good place to end on. So I'll see you in the next lecture.